Theorem of perpendicular axis. This theorem relates a moment of inertia of a laminar object about three mutually perpendicular and co-current axes. Here we know that x, y and z are mutually perpendicular and co-current axes. Here the two of them in the plane of the object and the third perpendicular to the object. Suppose we consider a z y plane, then x-axis will be perpendicular to this plane. If we consider xy plane, then z-axis will be perpendicular to this plane. If we consider zx as a plane, then y-axis will be perpendicular to it. The laminar object like a leaf or any two-dimensional object like a ring, a disc or any plane sheet, etc. Let us prove the theorem of perpendicular axis. So consider a rigid laminar object of any shape which is able to rotate about a three mutually perpendicular axes x, y and z. This axis x and y are in a plane of the object while the z axis is perpendicular to it and all the axes are co-current at point O. Consider a small mass element dm located at point P. The point P is any point on this laminar, rigid laminar object. Here we have to draw perpendicular to axis y and also to the axis x from the point P. So if I draw the perpendicular on a y-axis, so that will be a Pn, and also the Pm is perpendicular to the axis x. Now, as the line Pn is a parallel to the axis x, we can say that MO distance is equal to Pn distance, and that is x. Also, it is found that Pm is parallel to this y-axis and it is equal to NO distance, and that is also taken as a y. Now point DM is at a perpendicular distance, say OP, from the perpendicular axis Z, and it is found that triangle ONP or triangle OMP both are right angle triangle, and here we can apply a Pythagoras theorem, and therefore the distance from this perpendicular axis to this point element DM is OP, and it is given by square root of y square plus x square. So we can write here PM is equal to NO is equal to y distance. Also, Pn distance is equal to MO distance, that is the x distance, and OP distance is equal to square root of y square plus x square. As point DM is a very small object, we can calculate the moment of inertia of this DM about the x-axis as a Ix is equal to integration of Pm square into dm. Pm is a perpendicular distance from the axis of rotation, that is the x-axis, and this Pm is parallel to the ON, and that distance is equal to y, and therefore Ix can be written as integration of y square dm. Label it as a equation 1. Similarly, we can calculate the moment of inertia of this dm about the y-axis, and it is given by Iy is equal to integration of Pn square dm. This Pn is a perpendicular distance of this point object from the axis of rotation y, and this Pn is equal to MO, and that is equal to x distance, and therefore Iy can be written as integration of x square dm. Label it as a equation 2. Similarly, we can calculate the moment of inertia of this dm from that perpendicular axis z, and it is given by Iz is equal to integration of Po square dm. Po is that perpendicular distance from the axis of rotation, that is a z axis, and Po value is equal to square root of y square plus x square, and just substitute the value, so we get the Iz is equal to integration of square root of y square plus x square the whole square dm. Open the bracket, so we can write down the Iz is equal to integration of y square plus x square into dm. Open this bracket and do the integration, so we can write down the Iz is equal to integration of y square dm plus integration of x square dm. Now from the equation 1, integration of y square dm is nothing but the ix, and from the equation 2 we can write down integration of x square dm is nothing but the iy, and hence we get Iz is equal to ix plus iy. So this is a mathematical equation form of a theorem of perpendicular axis. Similarly, we can calculate the value of iy or ix. That is, ix is equal to iy plus iz. Here, y-axis and the z-axis making a plane, and ix is a moment of inertia about the perpendicular axis x. Similarly, we can calculate the moment of inertia about a y-axis if we consider the x and z as a plane and y as a perpendicular axis to it. So iy can be written as iz plus ix. Let us see some applications of theorem of perpendicular axis. Moment of inertia of a thin uniform disk about its diameter. So any axis passing along the diameter. Here id is equal to mr square upon 4. The moment of inertia of a thin uniform ring about its diameter, and let the r be the radius of this uniform ring. Then id is equal to mr square upon 2. The moment of inertia of a thin uniform disk about an axis tangent to the disk. So this is a tangent to the disk and it is in the plane of a disk, and let r be the radius of this disk. Then it is given by id is equal to 5 mr square upon 4. Here, to get this equation, we have used a theorem of parallel axis as well as the perpendicular axis. The moment of inertia of a thin uniform ring of a radius r about an axis tangent to the ring. So this is a tangent to the ring and it is in the plane of a ring, and it is given by id is equal to 3 mr square upon 2. Here also we have used the theorem of parallel axis and perpendicular axis.